All right, let's dive into a real-life molecular detective story. We're on a quest to identify culprits in a world that's completely invisible to us, the world of molecules. I mean, really think about that for a second. You've got some unknown powder or a weird substance in a water sample, or maybe a new compound you've cooked up in the lab. How on earth do you figure out exactly what it is? Well, that's the central mystery we're tackling today. Luckily for us, scientists have this incredibly powerful tool in their arsenal to solve these kinds of invisible mysteries. It's a single piece of tech that acts like the ultimate molecular detective. And this is why it's so important. This one technique is the thread that connects a crazy number of fields. I'm talking about everything from developing new medicines, to forensic teams detecting toxins, to monitoring for environmental pollutants, and even making sure the food you eat is actually what it says it is. Okay, so what is this amazing tool? The name of our molecular detective's secret weapon is mass spectrometry. But what does that even mean? At its heart, it's all about measuring the mass of a molecule. And by figuring out its exact weight, we can identify it and even get clues about its structure. You know, the easiest way to wrap your head around it is to think of it like this. Mass spectrometry is like a super precise scale. But instead of weighing, a bag of sugar, it's weighing individual molecules. It's literally a molecular scale. So how in the world does this molecular scale actually work? To figure that out, let's follow a single molecule on its wild journey through the machine. The entire thing really boils down to 4 key steps. First, we have to vaporize the sample, turn it into a gas. Then we ionize the molecules, basically give them an electrical charge. Next up, we separate them, and finally, we detect and count them. That's the whole game. Vaporize, ionize, separate, detect. And right here, you can see that whole journey laid out. The sample gets injected on the left, and it's instantly vaporized. Then, bam, it gets zapped by an electron beam, which is what ionizes the molecules. From there, a powerful magnet bends their path, separating them by weight, right before they slam into the detector at the very end. Now, this ionization step, this is absolutely crucial. See, you can't steer a neutral molecule with a magnet. It just won't work. So the machine blasts the molecules with electrons, which knocks one of their own electrons clean off. This leaves the molecule with a positive charge, turning it into something called a cation radical. And now it can be controlled. Okay, on to the separation part. I want you to imagine a racetrack, but with a really powerful, constant crosswind blowing sideways across the entire track. That wind, that's our magnetic field. This is where the magic of sorting happens. Just like on that windy racetrack, the lighter ions, think of them as the featherweights, they get blown way off course by that magnetic wind. But the heavier ions, they've got more momentum, so they're barely pushed aside at all. They fly much straighter. And that difference in how much they get deflected, well, that's everything. The machine is separating these ions based on what's called their mass-to-charge ratio, or m/z. By measuring exactly how much an ion's path was bent, the detector can calculate its mass with incredible accuracy. And that, right there, is the key to the whole identification. So once our molecular detective has separated all the evidence, we have to decode it. And the output from the machine isn't just one number, it's what we call a unique molecular fingerprint. And this is what the detective sees. It's called a mass spectrum. The horizontal axis at the bottom, the x-axis, that shows the mass-to-charge ratio, basically how heavy each piece is. And the vertical y-axis shows their relative abundance, how many of each fragment the machine actually detected. Now, to read this fingerprint, we're looking for a few key things. The molecular ion peak, that's the original molecule that actually survived the journey in one piece. The base peak is just the tallest one on the chart. It represents the most common fragment. And all the other little peaks? Those are the other smaller pieces the molecule's shattered into. And as the source material puts it so perfectly, the way a molecule shatters isn't random, not at all. It breaks apart in a very predictable, characteristic way. That pattern of fragments becomes a unique fingerprint that you can compare against a whole database of known suspects, or molecules. Let's look at a real example so you can see what I mean. This right here is the fingerprint for a molecule called hexane. You can see all the different fragment peaks that were detected. But way over on the right, you see that little peak labeled M+, sitting at a mass of 86. That's our molecular ion. That's the weight of a whole intact hexane molecule. So why all those other peaks? Well, It's because that initial blast of energy inside the machine causes the hexane molecule to shatter into smaller charged pieces. You can see here all the different ways it can break apart, creating fragments with masses like 71, 57, 43, and 29. Every single one of those pieces shows up as a peak on our graph. And when you put the two images side by side, it all just clicks. On the right, you see the molecule literally breaking apart, and on the left, you see the graph that the machine spits out from detecting those very same pieces. Notice how that fragment with a mass of 57 is the base peak, it's the tallest one, and that's because it's the most stable and common piece. It's a perfect match. The evidence lines up. And the level of detail is it's astounding. The machine is so sensitive that it can even spot different isotopes, heavier versions of the same element. For instance, chlorine always shows up as two peaks in a 3-to-1 ratio, while bromine shows up as two peaks that are almost the same height. These are like extra clues that help the detective lock down the case. So, we've seen how our molecular detective gets the job done. But what's the final verdict? What's the real impact of this incredible tool? Because at the end of the day, this isn't just some cool lab experiment. Mass spectrometry provides definitive, often life-changing answers. It's how investigators ID a poison at a crime scene. It's how new medicines are developed and tested. It's how we keep our environment clean and our food supply safe. We've created a tool that lets us see the invisible and identify the unknown with this astonishing level of certainty. And it really just leaves us with one fascinating question. Now that we can read the molecular fingerprint of almost anything, what mystery should we solve next?